Look at this photograph of a water strider. It rests precisely on the surface of a pond, suspended by tension, without breaking the liquid. We interact with properties like surface tension, pressure, and density as smooth, continuous realities. But matter is not continuous. So how do predictable macroscopic behaviors emerge from a chaotic, invisible domain of discrete particles? If we push past the surface, the illusion of stillness shatters. We are left looking at billions of microscopic molecules vibrating and colliding with each other millions of times every second. The properties we feel, the stickiness of honey, the shape of a raindrop, are not constants hard-coded into the fluid itself. They are emergent, collective thermodynamic behaviors driven entirely by thermal motion and microscopic collisions. For a long time, the ideal gas law was our primary tool for modeling fluid behavior, but it assumes particles are dimensionless points that never interact with one another. That works fine for thin, highly energized air, but it breaks down completely the moment we try to compress those particles into a dense liquid. A century ago, physicist Johannes Diederik van der Waals recognized two inescapable realities of actual particles. First, they take up physical volume. Second, when they get close to one another, they exert attractive pulling forces. He introduced a new equation with two vital corrections. A B term subtracts the physical volume of the molecules from the total space available, and an A term accounts for those attractive forces, which physically pull the particles together and reduce their outward pressure. By accounting for how molecules occupy space and pull on one another, this equation does something the ideal gas law cannot. It predicts exactly when a gas will condense into a liquid. These two microscopic corrections provide the mathematical bridge to the macroscopic world. We calculate density as a simple ratio, mass divided by volume. But look closely at this density map of a fluid. Because of relentless thermal motion, the distribution of particles is never perfectly uniform. It is a statistical average of constantly shifting clusters and empty voids. The severity of these localized density fluctuations relies directly on how compressible the fluid is. This is governed by the Ornstein-Zernike relation. When a liquid is heated to its critical point and becomes highly compressible, these internal density shifts grow so massive that they scatter visible light, turning a transparent liquid a cloudy white. This shifting microscopic architecture dictates how physical information moves through the material. A sound wave is simply a pressure gradient sweeping through a medium. The Newton-Laplace formula shows that the speed of that wave is strictly dictated by the fluid's density and its resistance to being compressed. Density represents the internal structural framework governing how mechanical force propagates through space. This image captures the folding, thick ribbons of pouring honey. That heavy resistance to shear forces is viscosity, fluid mechanics' version of internal friction. In a gas, this friction is not caused by molecules dragging against each other. It is caused by momentum exchange. As adjacent layers of gas flow past one another, individual molecules inevitably drift between the fast and slow streams. They act like passengers jumping between moving trains, transferring momentum and forcing the separate layers toward a uniform speed. This leads to a counterintuitive reality. When you heat a gas, the molecules move faster. They exchange momentum across the flow layers much more frequently, which increases the viscosity of the gas. Liquids operate under the opposite logic. Their molecules are tightly packed, locked in place by the attractive forces of their neighbors. To flow, a liquid molecule must stretch and snap past those bonds. Heating a liquid supplies the thermal energy needed to weaken those restraints, dropping the viscosity and allowing the fluid to slide. Albert Einstein formalized the connection between this macroscopic friction and microscopic randomness in the Stokes-Einstein relation. This equation proves that the chaotic thermal jittering of a single particle, its Brownian motion, is precisely tethered to the viscous drag of the surrounding fluid.
The energy a system loses to drag and the random thermal chaos of its molecules are mathematical reflections of the exact same physical mechanism. At the boundary between a liquid and a gas, another structural penalty appears. Molecules deep inside the liquid are pulled evenly in all directions by their neighbors, but molecules at the surface lack neighbors above them. This creates a net inward pull, forcing the liquid to shrink into the smallest possible surface area. This inward pull creates significant internal pressures. In this photo of champagne, look closely at the tiny bubbles forming at the bottom of the glass. The Young-Laplace equation dictates that the smaller the radius of the bubble, the higher the internal pressure must be just to hold back the crushing force of surface tension. This establishes an energy threshold for boiling. To form a new vapor bubble, the fluid must generate an entirely new surface against that inward pressure. This requires a specific energy input, often forcing water well past its boiling point before the first microscopic void can open. At an industrial scale, these microscopic boundary forces dictate heavy manufacturing. Consider this laser welding process on a steel cylinder. The laser creates a temperature gradient in the molten metal pool. In pure metals, heat lowers surface tension. The cooler edges of the liquid metal pull harder than the superheated center. This surface tension gradient, known as the Marangoni effect, physically drags the molten metal outward, producing a wide, shallow weld. But if you introduce just a few parts per million of sulfur to that steel, the entire system inverts. The sulfur binds to the surface, and under intense heat, the surface tension gradient flips. Now the flow vectors reverse, pulling the molten metal directly toward the center of the weld. A microscopic energy penalty and a fluid interface is powerful enough to reroute molten steel, dictating the structural integrity of industrial parts. Treating a fluid as a continuous, smooth material has hard limits. If we shrink our perspective to a microchannel, where the width is equal to the mean free path of the molecules, the particles collide with the walls more often than each other. The Knudsen number maps this threshold. Cross it, and macroscopic concepts like viscosity stop making physical sense. Biological life evolved directly against these constraints. When plants transitioned from water to land, they faced a severe mechanical problem. They had to pull heavy water upward from the soil while extracting carbon from a low-density atmosphere that offered zero buoyant support. This microscopic cross-section of plant tissue reveals their evolutionary compromise. A plant needs wide xylem vessels to maximize viscous flow efficiency, following the Hagen-Poisson law. But wide pipes are dangerous. Under intense negative pressure, a tiny air bubble will expand and snap the water column. Narrow pipes, protected by the tight curvature of the Young-Laplace equation, can withstand much higher tension without breaking. The varied diameters of these vessels show how evolution continuously optimizes biological structures against the unyielding mechanical laws of fluid dynamics. A persistent misconception in biology is that all cellular processes are neatly compartmentalized inside lipid membranes, like the nucleus or the mitochondria. But inside the cytoplasm, proteins with multiple weak bonding sites can cluster together. When their concentration hits a critical threshold, they spontaneously separate from the surrounding fluid into distinct, membraneless liquid droplets. Cells actively utilize the principles of density, surface tension, and viscosity to generate these biomolecular condensates. By concentrating specific enzymes in one place, these droplets increase the frequency of molecular collisions, ensuring biochemical reactions occur at the speeds required to sustain the cell. From the precise control of supercritical solvents in chemical engineering to the dynamic protein droplets organizing our immune response, fluid dynamics operates on a strict, universal logic. The predictable, continuous behavior of the rivers, atmospheres, and liquids we interact with every day is the elegant mathematical consequence of trillions of microscopic compromises.